What are differential equations? Well, they're based on calculus. So if you haven't had at least enough calculus to know what derivatives are, I can't really explain what differential equations are because they're based on derivatives. But if you have had some calculus, this is going to be how I would explain, say, on the first day of class of a differential equations class, what differential equations actually are. First of all, you know what equations are, right? The kinds of equations you'd study in like a basic algebra class. Things like 3x minus 6 equals 0, or n squared equals n, or x squared plus y squared equals 25. In these kinds of equations, the variables stand for numbers. And when you're solving the equation, you're coming up with a number that can go in place of the variable to make the equation true. Like for 3x minus 6 equals 0, x would have to equal 2. For n squared to equal n could be either 0 or 1. 0 squared equals 0, and 1 squared equals 1. For x squared plus y squared equals 25, there are many possible solutions. They're all pairs of numbers, a number for x and a number for y to go with it, that make the equation true. You could have 0 for x and 5 for y, or negative 5 for x and 0 for y, or 3 and negative 4, or 2 and the square root of 21, or there are infinitely many possibilities. They all form a circle of radius 5 centered at the origin. So anyway, those are the kinds of equations you're used to from basic algebra. So in differential equations, the variables that you're trying to find values for stand for not numbers, but functions. And so solutions are functions that you can put in place of the variable to make the equation true. For example, y prime equals y. So here you're trying to figure out, okay, what function could y stand for so that y prime, the derivative of y, is equal to y itself? Or dy dx equals x plus 3. What can y be as a function of x so that the derivative of y with respect to x is x plus 3? Or d squared x dt squared equals 12t squared. So here x would be a function of t, and you want to know what function that would be so that the second derivative of that function with respect to t is equal to 12t squared. And these are really simple differential equations. They do get more complicated than this, but this just gives you an idea. In each case, to solve the differential equation, we're trying to figure out what function can go in place of the y or the x or whatever. Now let's take a closer look at this first example. Y prime equals y. So here we're looking for a function where the derivative of that function, y prime, is equal to y itself. Do you know a function like that? If you've studied calculus, you probably encountered a famous function that has this property. And that function is e to the x. It is its own derivative. So if y is e to the x, then y prime would be the derivative e to the x, and y prime would be equal to y. Is that the only possibility, the only function that works here? Well, not really. I can think of y equals 2 times e to the x. Remember, the derivative of a constant times a function is the constant times the derivative of the function. So if y is 2e to the x, then y prime would also be 2e to the x, so y prime would be equal to y. Y could be equal to 10 times e to the x, or in general, y could be equal to any particular constant, c, times e to the x. So for the general solution, we could just say y equals c e to the x, where c stands for any constant. So that would be the general solution. And with differential equations, sometimes we want the general solution like that. And sometimes we're looking for one particular solution that satisfies some particular initial condition. Like, for example, what's the particular solution to this differential equation so that when x is 0, then y is 42? And the answer is y equals 42e to the x. Because if you put 0 in for x, then y is equal to 42 times e to the 0. That would be 42 times 1, which would just be 42. And this sort of thing where the general solution involves a constant c is something you've seen before if you've studied antiderivatives or indefinite integrals, because you're used to having your antiderivative or your general indefinite integral end with a plus c on the end. So like dy dx equals x plus 3 means we're looking for a function whose derivative is x plus 3. We want antiderivatives for x plus 3. And so that would be 1/2 x squared plus 3x plus a constant. That constant could be any particular number, and you'd still have a function whose derivative turns out to be x plus 3. So if you've studied antiderivatives or indefinite integrals, you've seen this situation before where the general solution has an arbitrary constant in it somewhere. And so with solutions to differential equations, they often involve constants. There's a c in there somewhere. Now, instead of just y prime equals y, think about y prime equals some particular number times y. Y prime equals k times y. So if you remember from calculus that derivatives represent rates of change, this is saying that the rate of change of y is proportional to y itself. That is, how fast y is changing or growing is proportional to how much of y there actually is at any given time. And there are several situations in the real world that work this way, or at least approximately can be modeled like this. For example, compound interest. The amount of money in an interest-bearing account is growing as the interest gets added on. And the more money you have, the more interest gets added on, because like 5% of a large amount is more than 5% of a small amount. So the more money there is, the faster that amount grows. It grows at a rate that's proportional to the amount that's present. Or think about the population of bunny rabbits in a meadow. The more bunny rabbits there are, the more baby bunny rabbits will be born, and the faster the bunny rabbit population is going to grow. Or maybe the amount of bacteria in a bowl of stew that's been left out of the refrigerator. So this kind of situation, where the rate at which something is growing is proportional to the amount of the thing present, can be modeled by this particular differential equation. So that's an example of where differential equations come from in the real world. They come from when you have a situation where you have a relationship between how much of something there is and how fast that thing is changing, and you model that with a differential equation where the y prime, or the derivative, represents the rate of change, and it is somehow related to the independent and or the dependent variables in the situation. And by the way, this is sometimes an oversimplification. Like the population of bunny rabbits in the meadow is going to probably depend on other factors, like how many bunny rabbits the meadow has room for and whether there are predators and other factors like that. So sometimes it's not quite so simple, but we're keeping things simple right now for this introductory video. But the solution to this differential equation would be for y to equal c times e to the kx. Because if that's what function y is, then the derivative of y, well, the derivative of a constant times a function is the constant times the derivative of the function, and the derivative of e to the something is e to the something times the derivative of the something. So if y is c times e to the kx, where c and k are both constants, then y prime is going to be c times e to the kx times k. And so that's going to be y times k, ky. So that's it for a real basic introduction to what differential equations are. Now, if you were taking a whole class in differential equations, you'd study things like Well, there's various different kinds of differential equations that can be classed in different ways, and that's important because that tells you what kinds of solutions you can have and how you might go about finding those solutions. You learn methods for solving different kinds of differential equations. You learn all sorts of techniques for solving them analytically, that is, using techniques of algebra and calculus and so forth for coming up with the formula for what the solution actually is, what function, a formula for that function that satisfies the differential equation. But you might also study some numeric methods of solving by doing lots of number crunching, come up with an approximate values of solutions, or qualitative solutions, figuring out if you can't tell exactly what the solution is, you can at least get an idea of what kind of a solution it has, and that gives you an idea of what's going on in general. In the long run, is the bunny rabbit population going to just get infinitely large or die out or level off at some level? You'd study probably some geometric interpretation, some graphing, how you would graphically represent a differential equation itself or the solution or a system of differential equations. And of course, you'd study some applications, some situations that you would model and study and deal with by setting up and solving differential equations. So that's it for this video. If I get around to it, if I feel like it, I'm going to be making maybe some more videos that go on from here.